Welcome to the Physics of Complex Systems laboratory. From a physics perspective, a complex system is a system with a complex energy landscape that has many local minima. And so as such, by nature, it is metastable. And so these systems we observe all around us. They occur, for instance, in biology, epidemiology, earthquakes, friction, glasses, transportation systems, but also in deep learning. And what we want to do in our group is to understand some of these systems, and in particular we want to work towards better earthquake predictions and a better understanding and maybe an improvement of deep learning. And to do so we use different techniques. We use arguments from statistical physics, we use scaling arguments, but we also use numerical simulations and we perform high-performance simulations. The first topic we study is friction between solids. And friction between solids, the question is essentially very easy. You put two solid objects together and you impose a force or a displacement and you ask what happens. And one of the things that can happen is stick-slip, that is sketched here on the top right. And during stick-slip, when I impose a very slowly increasing displacement and I measure the force, we observe periods during which the two objects are perfectly stuck together, punctuated by slip events during which the force drops macroscopically. And these are essentially what earthquakes are. And so what we want to do is we want to have a prediction of this curve, and this is currently not possible with the knowledge we have in the literature. And what we know from the literature is that these slip events, they are like a propagating fracture. But what we don't know from the literature is how these fractures are nucleated. And this is what we want to understand. And one of the reasons it's not known in the literature is that disorder and inertia are often ignored. We were able to make a scaling prediction for the force displacement curve that is sketched. But this opens actually a bunch of questions. So first the question is, how does this relate to classical measurements in friction? The second question is, how does thermal activation change our scaling relation? And the final question is, can we make a prediction for these exponents? And these three questions we hope to answer with your help.
The other branch of research of our group is machine learning theory, with a particular focus on deep learning. What is deep learning? Deep learning is a subset of artificial intelligence that uses artificial neural networks inspired by our brain in order to learn a task from a large amount of data. For instance, you can build a neural network that can distinguish between cats and dogs. Recently, this field has exploded thanks to the availability of larger and larger amounts of data and to computing power. However, despite a huge practical success, understanding how and why this machine works is still an open question. In the group, we study questions like, how many data does a neural network need in order to learn a task? How does this depend on the network's architecture and on the data structure? For instance, recently we published a work about how the compositional local structure of data affects the performance of modern neural networks. Another topic we are actively investigating is the training dynamics. Indeed, these algorithms consist in a stochastic trajectory in a complex energy landscape. And this setting has many correspondences with the statistical physics of complex systems.
To tackle problems in deep learning theory, we use tools from statistical physics. For example, in one of our works, we made a direct analogy between over-parameterized neural networks and a very special phase transition that is found in complex systems. Another central idea in physics is the one of symmetries and invariances. We have several lines of research where we are trying to show how, by leveraging invariances in the task, you can improve the performances of neural networks. For example, the artificial neurons can align to the most informative directions in the input space, or you can show how state-of-the-art neural networks can learn to be stable to smooth the formations of the input images. To solve all these problems, we use tools that are both theoretical and numerical. For example, we have projects that can be tackled with ideas and approaches of theoretical physics, instead other projects that can require a lot of computer simulations. So if you want to know more about the projects we work on, please contact us and we will be very happy to welcome you in our group.